Hello, and welcome to Civil Engineering 18 Senior Design presentation for our project, the replacement of bridge number 02968. In 2018, the Connecticut Department of Transportation identified the bridge across Pendleton Hill Brook as being in need of replacement. For our project, we focus on the replacement phases of the bridge, as well as replacing the abutment designed for the new bridge deck. The replacement phases include rerouting traffic around the bridge, creating a detailed list of replacement stages, and designing a cofferdam and bridge scaffolding to be used during construction. First, we will go over the existing conditions of the area. The surrounding area is relatively flat, with only a small gradient across the bridge. The brook is fairly quiet, averaging a foot deep, with a 9.3 cubic feet per second flow. Here we have our map for our detour routes. With 1,700 cars a day being rerouted, it's important that we have enough space for that traffic, so we split it up. This means that traffic will be better absorbed by the surrounding roadways. These roadways near the bridge have also been safe, with less than 100 crashes occurring in the past 5 years.
Next, we took a look at structural analysis calculations to determine the capacity of the existing bridge, as well as the demand the new bridge would have to handle to ensure structural adequacy. We utilized the ASCE manual as well as AASHTO code to do so. The live load of 2.5 kips per square feet was calculated assuming 4 heavy trucks driving over the bridge. An impact factor of 0.3 was calculated to let us accommodate for the bouncing or swaying of the trucks in this figure. The dead load of 3.6 kips per square feet was kept relatively low due to an efficient design. The snow load of 21 pounds per square feet was calculated accounting for flat loads and snow drift loads, which are quite common in Connecticut. Finally, the earthquake load of 2 kips per square feet was determined using the USGS seismic design maps that use latitude and longitude to determine earthquake spectral response acceleration. After getting our load conditions, we evaluated the LRFD load combos and found the worst case scenarios our bridge would have to face. We took this information from these calculations and other metrics to help evaluate our initial design alternatives. But before we could work on these design alternatives, we have to remove the existing bridge. This was relatively straightforward due to there being strict guidelines and specifications in place from the CT Department of Transportation for this process.
In relation to the cofferdam, the selected material remained constant per the advice from our sponsor. However, the amount of material required depended on where the cofferdam was located. Rather than have the cofferdam extend to either bank, it was discussed that the cofferdam could restrict stream flow, permitting water only to flow through a 36-inch pipe that was backfilled between the cofferdams. Given the amount of environmental disruption this would cause, this idea was not considered. For the abutments, first we considered how many abutments were actually needed for the bridge, and we decided only 2 were necessary because the bridge is relatively small, 1 abutment at each end. Our abutment definitely needs a bridge seat to hold the deck and a back wall to support the bridge seat. We decided we didn't actually need physical columns for support, a short wall would be a sufficient pile. Rather than designing a footing ourselves, we decided to design the abutment to rest on top of the existing foundation, as it is adequate to support the bridge. This would avoid the unnecessary cost of digging to install new footings. We also decided the wing walls on the sides of the abutments were not necessary, as the embankment is directly behind the bridge. Considering which abutment components we needed and which we didn't, a basic gravity abutment fit our need the best.
Moving to the final design, utilizing the Engineering Handbook and Connecticut DOT Sheet Pile Design Manual, the cofferdam was designed. The cofferdam will be made out of PZC-13 to support the maximum moment of roughly 4,700 pound-feet. PZ-13 is commonly utilized for sheet pile walls and will be able to resist the impact force as it is hammer driven 5 feet into the soil. To account for the 100-year flood levels, the wall will be exposed 6 feet. Given the soil conditions, the wall should fall into place relatively easy. However, misalignment is common during installation, especially considering the relatively small work area. After the main deck is removed, the cofferdam will be added to both banks, totaling 80 feet of wall on the west bank and 90 feet of wall on the east bank. For the new abutments for the bridge, we performed a structural analysis to determine the loads acting on the bridge, as well as the earth pressure on the abutments. Using these forces, we were able to obtain an abutment shape and size that would support the loads. The total height of the abutment is 6.58 feet with a 2-foot bridge seat. The pile and back wall are designed to withstand the earth pressure from the embankment in addition to the bridge loads. Finally, by closely following all applicable OSHA and ASTM regulations, the bridge scaffolding was designed. Per requirements, all wood used will be 150 pound-feet PSI construction-grade lumber. The final dimensions will be 35 feet long and 5 feet wide, with scaffolding being put on both sides of the new decking. To minimize damage to the precast decking, B16 coil loop inserts will be drilled into the decking to allow for ease of scaffolding installation and removal. Under these design assumptions, the maximum load the scaffolding will hold was calculated to be 4,375 pounds. Thank you from all of us at Similian and Quays.